I've got the distinct pleasure today to introduce the Faculty Senate Distinguished Lecturer, and I think you're really in for a treat to hear Paul Martin's talk. But to give you a little bit of a background on Paul, he got his degree in mathematics, his BS degree at the University of Bristol, and then he went up to Manchester and got a master's degree, I guess, in applied math and fluid dynamics. And he figured I was getting a little too applied, so he went ahead and then got his PhD in pure mathematics. And then he stayed on the faculty at the University of Manchester, and much to the chagrin of many of his colleagues there, CSM was able to lure him here in 1999, and he's certainly been an extraordinarily productive faculty member here ever since. Paul's got an enviable publication record of about 110 publications, and he's also got a book out, and he's a glutton for punishment because he's actually editor of 3 different journals. Okay, well, you aren't teaching enough, clearly. but the thing that I think was most interesting, I had the luxury of looking through some of the nomination papers for Paul, and there was one thing in there that really struck me that I think resonates very much with other faculty members, and I think it's a really good indication of why he was chosen to give a distinguished lecture. And that was, one of his colleagues said, the most interesting thing about Paul is that on a Friday, I can ask him a question, and it's a tough question. He says, and Paul's answer, after thinking about it a minute, he says, let me think about that. Okay? And lo and behold, this colleague would come in on Monday morning, and in the words of this recommendation, there would be 10 pages of latex script from Paul solving that particular problem. Okay? And I read that and wept. but in any event, I think you can see we're in for a real treat today, and Paul's going to talk to us about what is applied math really, and why do we need it really, and it gives me great pleasure now to introduce Paul.
Okay, so I'm going to put my beer here. So. Okay, well, first of all, I should thank Tony for the very kind words, and I should thank you all for coming. You probably have 2 questions. So the first one is, how did he get this, to give this lecture, and how did he choose that title? Maybe that's not very exciting. Mathematicians like symmetries. I would like to really stand here, but then I'd give myself
You can stand on top if you
okay, so how did I come to be here? I mean, how did I come to be standing here? Well, for that, let's see if this works. Okay, I can thank my campaign manager. I was a reluctant candidate, but anyway, he got me nominated, Dinesh Mehta. Thank you very much. I don't know where you are. Oh, okay, thank you. I thought maybe you would decide not to come. So, and then the title of my talk, I'll explain to you a little bit later on where that came from. But the reason I have anything to talk about really is because of my wife. So I'll thank her for that now, otherwise I'll forget. Now, I should start with a confession, which is, if this thing works, oh, here we are. So I'm a mathematician, so this is I have to confess that. So mathematicians are notorious, or let's say the mathematicians are at the strange end of the spectrum of humanity, usually. Of course, that means that, like everybody else, in fact, they are humans, of course, but that means that they're prone to naked prejudices and rash generalizations and bizarre opinions. So I'll give you some of those later on as we go along. But anyway, I'm a mathematician, right? So there's nothing I can do about that. Now, in fact, I'm an English mathematician. So here's a map of Britain. So let me start to qualify what mathematicians do, right? And what they like to do is they like to simplify things. This is the first thing they like to do. So of course they like a simple life. That's why I have to thank my wife. She makes sure that my life is simple. So they like simpler problems, right? So what typically happens in my job, if you like, or part of my job, is that someone will come and knock on my door and say, I have this problem. Right? I don't mean a psychological problem. I can't help those. But when problems come along, they're usually more complicated than they need to be. Right? And part of what we do, if you like, is to make problems simpler. Right? Try to remove extraneous parts of problems. So they like simpler problems, but not too simple. So you don't want to do things that are really easy. Right? That's no fun. So they like simpler equations. Okay? I'll say more about equations later on. But they like simpler equations. So if an equation, if you like, looks complicated, then they will be inclined to try to simplify it. They like simpler notation. Right? This is a big problem, especially with graduate students from non-math departments. They like to bring problems and show you problems, and they're festooned with ornamentation on their symbols. Right? So this is a bad thing. Right? The first thing you should do if you can't do something is clean away the debris, clean away the junk, right? And try to make the problem look simpler. Not just be simpler, but look simpler. And of course, they like simpler geometries as well, right? So there's a famous joke about that's told about mathematicians or about physicists of various kinds, and the punchline of the joke is, consider a spherical cow. So if you've never heard that joke, you can go and look it up on Wikipedia. There's a Wikipedia page on spherical cow. It's about this joke. But the idea is to simplify the geometry. Okay, so I simplify the geometry. Here's a map of England. Okay? I told you they like to simplify. So I only kept in the essential details in this picture. Right? So I was born in L. Right? So more precisely, I'm a Cockney. So if anybody knows what that means, it means that you were born in a certain part of London. Okay? And mathematicians like it because it's well defined. Right? And the definition is you have to be born within the sound of Bow bells. So Bow is a particular place in the east of London. There's a church there with bells. So if when you're born you could have heard the bells, then by definition you are a Cockney. Of course, the propagation of sound depends on atmospheric conditions, so it's not a very precise definition. Okay? But at least it's a definition. So I was at the U of M for 24 years, as Tony just told you. So I went there as a graduate student. I have a PhD in mathematics, actually, not pure mathematics. That was an insult, by the way. But never mind. And as he said, I moved here in 1999. I'm a grandfather. So that's my grandson. So that tells you now that the word distinguished means old. Right? And I don't do any of these things. So unlike most people in Colorado, right, I never go outside. Right? So, and I take this quote from Winston Churchill. So he said, don't stand up if you can sit down, don't sit down if you can lie down. So he lived to be about 90, and he had whiskey every morning for breakfast and smoked cigars, and nevertheless. Okay. All right, so now I classify again. So now I'm a British applied mathematician. So I'm going to explain what this means, but to be a British applied mathematician, you don't have to come from Britain. That's the first thing, right? So it's a kind of style of applied mathematics, which I'll try to explain to you. So of course it's pervasive in Britain, but it's also common in some other countries. So you'd often find it in parts of Canada, Australia, and various other colonies, if you like. Okay, so now I have to explain to you a little bit, and I think one of the things I'm supposed to do in this talk is tell you a little bit about me, right, and why I have the prejudices that I have. So in the 1970s, when I was went to university. So I was an undergraduate. I became an undergraduate exactly 40 years ago. Right? So I told you I was old. So in those days, the goal of British universities was to make specialists, right? Not to educate. It was to make specialists. Right? That's the way you should think of it. Okay? When you applied to university, you weren't admitted to the university. You were admitted to a department. Right? So you'd already decided what you were going to do before you got there. And then in 1979, along came this person. Anybody recognize this person? So this is Margaret Thatcher. And one of her, let's say, unstated goals was to do the universities down, right? So she didn't really approve of universities and what they did, okay? This is despite the fact that she went to Oxford and she was a research chemist, right? So she had a job as a research chemist, but she gave that up as soon as she managed to find a rich man to marry, right? That's what she did. And then she went into politics. Right? Well, anyway, I shouldn't go on about Margaret Thatcher, right? But all right, so in my last 2 years of high school, so this is from 16 to 18, what I studied was mathematics. I put an S on math because in England we say maths, not math. So I studied mathematics and physics and nothing else, right? Nothing else. Then, as an undergraduate, I went to Bristol University, which is on my map of England. It's a dot to the west of L. So as an undergraduate, I studied mathematics, nothing else. I didn't do anything else. Right? Then, as a graduate student, so now I've moved up to Manchester, I studied applied mathematics, right? And nothing else. Right? So all my classes that I ever took were always within math departments. Okay? I don't know why I'm telling you this, it's just that we do things differently, or we did things differently in Britain, right? So you don't have to always do things the way that maybe you think they're going to be done. But you should keep in mind that the goal was to make specialists, right? Not to educate. So I don't know anything about English or French or geography or nature and human values or geology or any of that stuff, right? And of course, the result of this is I'm a specialist in applied mathematics. What else could I do, right? So that's why I talk about this, right? Because I don't have anything else really I can tell you about. Anything that you'd be interested in anyway. Okay, but now let me try now to explain what applied mathematics is, all right? So it's pretty hard to define this, right? So this is perhaps the best place to start. Right? So some of you know where this will come from. So I don't really know what it is, but it's, what did you say here? I know it when I see it. Right? So maybe some of you know where this comes from. So this Justice Potter Stewart was from the US Supreme Court. And when he was asked to define hardcore pornography, this is what he said. There was an obscenity trial, and so they had to decide whether something was obscene or whether it was free speech. Right? And of course, there's a Wikipedia page on this as well. Okay, but so now, if you look, there's lots of people have tried to define what applied mathematics is, and I don't want to advocate any one particular definition, but I think this is a decent working definition of what it is. Right? So I read it: using mathematics as a tool for thinking clearly about the world. So I think that's a pretty good start, all right? And I'll try to flesh this out as we go along. Another place to look would be on the masthead of the Siam Journal on Applied Math, right? So this is probably the top journal of applied math in the country, on the planet maybe, right? So I can say that because I'm an editor, right? So, but read some of the words here. So it says the Siam Journal is an interdisciplinary journal. So that usually means that the papers in that journal are meant to be not just mathematics, but mathematics related to something else, maybe physics or engineering or biology or something like that, right? So it usually involves something else, right? And then I carry on. Continuing research, using methods that are of mathematical interest, right? So the difference here now is that it's not just using mathematics, right? The mathematics itself is supposed to be interesting, right? So Typically that means you're doing new mathematics in order to understand, let's say, a physical problem. From now on I'll say physical problems because that's really what I know about, but it could be problems in other areas as well. Biology especially is a big area, a growing area from the point of view of applied mathematics. So that's kind of idea of where we might try to define applied mathematics, if you think it's worth defining. So maybe another place to look then is to see what applied mathematicians actually do, okay? Apart from sitting in their offices twiddling their thumbs, right? Or grading complex variable exams, right? Okay, so I'll start here. There's my wife again. So the context of all this, of course, is science, right? Or let's say science, okay? So when we think about how science works, right, the usual way we would set this up, the way we might think about how science progresses is you think of some kind of physical phenomenon, right? And maybe you've done some experiments and you think there's something interesting going on, okay? So then what you would do, this is the usual way we think about this, this is how we would teach students how science is done, right? It's not always how it is actually done, but this is how you would teach, I think. First thing you do is you say, well, I'll try to write down some equations which we think represent the physical phenomenon, okay? That would be the first thing you would do. And I'm going to flesh these out as we go along, so I don't want to say too much at the moment. Then the next step would be to solve the equations, okay? Whatever that means, right? And then, having solved the equations, right, we would try to make some predictions by looking at the solutions, try to make a prediction, right? Maybe a prediction of something that hasn't been observed before, right? Or maybe make it a prediction where you can try to explain experiments that have already been done. Okay? So then we would make comparisons with experiments, right? Either future experiments or past experiments, right? And then, of course, they don't usually agree, right? So then you have to decide for yourself what you're going to do next, okay? And usually we would kind of complete the loop and we would go back to the beginning if necessary, right? Maybe modify the equations that we started with, right? Or maybe go back and check the experiments if you don't trust the experimenter. Okay, so this is the kind of standard way to think about how science is done. So a good question to ask at this point, and people have asked this question, is why bother with equations? What is it about equations that we get involved with? Why do we do that? Right? And this is a quote from Wigner, who was a Nobel Prize winner in physics, right? And I think this is pretty good. Right? The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. So the idea there is that maybe mathematics is not the right language. Maybe there should be some other language, and we just somehow stumbled across mathematics. Right? So it's kind of a philosophical thing. Maybe we shouldn't be thinking about that at Mines. Right? but it's a strange question to ask, right? Once you think about it, you say, well, how come it is mathematics that we do this? So, but usually the way we think about this then is we think, right, that if we can distill a phenomenon into equations, right, and then make predictions and they agree, everything hangs together nicely, then we think to ourselves, oh, well, maybe I understand the phenomenon. I can actually understand what's going on here because I've been able to convert it into some equations which make predictions, which then everything fits and agrees. Right? I'm mindful of the clock up here. It'd be much better if the clock was over here. But you know the golden rule when you give a talk is never use more time than you're given. Right? I'm talking to the students here. Okay, so then at this point I did ask the committee that gave me this honor whether I was allowed to show any equations. And apparently I am. So what do we do with equations? Why do we write them down? Well, to me, equations help you clarify and simplify what's going on. Okay, so to me, see, supposing somebody sends me a paper to referee, right? So now I'm talking to the faculty. What's the first thing you do? To me, the first thing I do is I look at the references, right? And then I start to read section 2. right? I never look at diagrams. I never look at graphs. I'm not interested in graphs. I always look at the equations. That's the only thing that matters. So that probably makes me different to many of the others, right? Because to me, that's where I'm going to see if the author and I can understand what's going on by looking at the equations. I once was at a thesis proposal in your department, where the student sent me the thesis proposal, and this is a good student. I'm not saying anything bad about the student. So the student sent me the proposal, and I looked at the proposal, and then the student came to me before the exam and said, you didn't have any questions before the proposal about my document. So I said, well, there's no equations in it. Well, how can I ask you any questions? There's no equations. And the student said, well, I left out all the equations to keep it simple. I thought the readers in my department would think it was simpler if there weren't any equations. Right? So that's the opposite to how I think. Right? So everybody's different, of course, and I'm not saying anything bad about the student. Okay, so some equations are fascinating, I think I can say this, provocative or even lovely. All right? So I'm going to give you a few equations now, if this thing works. Okay, so everybody knows this one, right? Everybody at Mines knows this one. So I don't have to say any more about that, right? How about this one? Everybody in my complex variables class knows this one, right? So this is, well, of course, I don't have time to explain it to you if you don't understand it, but most undergraduates would know this equation from calculus. What about this one? I think this equation is really fascinating because, okay, so if you don't know anything about complex numbers, you can shut your ears for a moment. So this says I take the complex number I and I raise it to the complex power I, and I get a real number out. Right? So some students think this is really fascinating, and you can hook people on mathematics by formulas like this. Right? Other ones just think this is just a complete waste of time, and they go off into mechanical engineering or something. I chose mechanical engineering at random there, right? Okay, now I have this one. So now I'm onto a partial differential equation. So this is Laplace's equation. So I probably know more about this equation than is good for me. Right? So don't. So this is a good friend of mine. And now I move on to, this is a popular equation. So you probably all know this one. This one has a different, there's a special version of this just for School of Mines, which is this one. It would be nice if the dollars that came from the FTEs went back to the department somehow, but they don't usually somehow. But that's another lecture. Here's another one. This is for Andre. So this equation that wine is equivalent to food here is governed by the CNRS. This is the French, roughly the French equivalent of the National Science Foundation. And this works because if you have a grant and you take someone out for dinner, you can charge wine to the grant. That's true, right? You can't do that in this country. But I prefer a relative of this equation. I prefer this one. So now I can have my beer. So who do you think this one is due to? I attribute it to Inspector Morse. Do we know who that is? Anybody know who Inspector Morse is? Anyway, I can confirm that all these equations are true. All right, so now let's come back to what I get up to. So the first step, you remember, was taking the physical phenomenon and then trying to write it down, to model it, we would call it modeling, in terms of some equations. Okay? So sometimes this is an easy thing to do. All right? For example, if you're interested in the flow of an incompressible viscous fluid, you'd write down Navier-Stokes equations. That's the first thing you'd do, probably. Okay? But the trouble is that although you know what the equations are, they're too complicated and you can't deal with them. Right? So nobody knows how to solve the Navier-Stokes equations in general. Right? So usually you make some simplifications. Right? maybe you say, well, the fluid isn't really viscous, so I'll throw away the viscosity terms. Or maybe you say, well, the flow is really slow, so I'll throw something else away. And you always try to simplify problems. Okay? So the question here is that when you do this simplification, right, you've got to decide what it is you're going to throw away and what you're going to keep. Right? Obviously, you want to keep enough so that you're making a good job of representing and modeling the phenomenon that you're interested in. Okay? So you don't want to throw everything out. Right? So if you're interested in the flow of treacle, right, some black molasses or something like that, right, you don't want to say that the flow isn't sticky at all. Right? That would not be a good model. Right? You might get some equations that you can solve, but it wouldn't represent the phenomenon that you're interested in. So this is something where applied mathematicians have skill, let's say, right, and experience. Okay, so the idea of taking a physical phenomenon and replacing it by equations, that is a skill. Okay? And it's not something, it is a skill, it's not something where you always know what to do. All right? So, and it's hard to teach this. So we do try to teach students this, but it's difficult to teach this, right? Because a lot of it relies on experience, right? Seeing similar problems before or noticing how other problems were simplified. Right? That's why modeling is often taught in a kind of case study basis. You often get dug in deeply into particular physical problems and you try and represent them by equation. You learn by doing it. So I take a problem here that I worked on with John Berger, I forget how many years ago now. But this is an interesting physical problem. So the object on the left there is meant to be a piece of an overhead cable, overhead power line. Right? So overhead power lines are complicated things. Okay? And you can see a kind of sketch of what's going on there. It's a circular cylinder. That's great, right? Simplify the geometry. It's already simple. Okay? But the composition of the cylinder is complicated. Right? And you all know what a piece of wire is like a piece of rope. Right? It's a complicated thing. And in these problems, what happens is that the central cylinder here, this little one here, I don't use laser pointers because I'm colorblind. I can't see them. So this one here, right, is typically made of steel. Right? And then all these little helical strands, right, they're usually made of, in my country, they're called aluminium. Right? So aluminum. Okay? And you can see that there's this kind of helical structure, and each concentric layer here, the helices go in opposite directions. Okay? So you should agree that that's a complicated structure. So the problem that John and I worked on was a problem where you take these overhead power lines, and then you try to send a kind of disturbance, a wave that propagates down this cable. Right? And the idea being that if you can send some kind of pulse that goes down this cable, if there's a defect, a break in one of the little strands, there'll be something that will be reflected, and you might be able to look at that and figure out what it was and where the break was. So you could use this to monitor the degradation of cables. Right? So that was the idea. But obviously, if you wanted to write down the equations of this, you could do this, right? You could go right in here like this. You could say, oh, I take this little cable here and I write down the equation of that little wire there, and then I do it for this one and this one and this one, and I try and stick them all together with boundary conditions and all this stuff. That will be completely hopeless. Right? You've got no chance. So you've got to do something to kind of average out the problem, to simplify the problem, okay, so that you get some equations that you can handle, okay, but they've also got to represent the physics. All right? So it's that balance between keeping the important things in, getting some equations that you can model and solve. Okay? So that's what we did some years ago. So a good feature then of the British system, if you like, the British applied math system, is that all this kind of physical stuff is completely embedded in the mathematics curriculum. Right? You never get away from fluid mechanics. Like Tony said, I have a master's degree in fluid dynamics and applied mathematics. That's the name of the degree, right? And it's a complete mixture of complicated fluid mechanics, complicated mathematics used to understand the fluid mechanics. So that's a good thing. And the way that the British curriculum would start, remember that the goal there is to make specialists, right? Not to educate, it's to make specialists. The goal there, the way this would work is that you'd be doing your mathematics, you'd be doing differential equations and so on. The first thing you'd start with would be Newtonian mechanics, right? Newton's laws, F equals ma. Okay? You do that because that leads to ordinary differential equations. And then you get more and more complicated. Okay, what about American applied mathematics? Well, that's easy because there never used to be any. So before the First World War, right, there was practically none in this country. Right? Practically none. I can think of some counterexamples, but I don't want to spend the time on that. But I can come back to this later on. So, and the reason for that really is that, so there were universities, right, and they were generating good mathematics students, but if they wanted to do PhDs, they nearly always went to Europe to do their PhDs, right? And they'd go to Europe, typically to Germany, right? Until maybe 20 years ago or so, if you did a PhD in mathematics in this country, you also had to be proficient in a foreign language, right? And that's the reason why, right? Because students would typically go to Europe. I don't mean go to England. They'd go to Europe, typically Germany. That was the hot place for mathematics at this time. Okay, and they would get a PhD in pure mathematics, and they'd come back, and so that's what they would teach: pure mathematics. They wouldn't go to England to do a PhD in mathematics because there were no PhDs in England. The PhD wasn't introduced in Britain until after the First World War. In this country, it goes back to the 18th century. Okay, so between the wars, there was some applied mathematics, right? But not very much. Right? I'm keeping my eye on the clock here, so I'll have to go a bit faster. Perhaps I mentioned that at that time there were some very good research labs associated with companies. Right? There still are a few of those. And maybe to mention a few of the people that came over in this period. So there's Richard Courant, who went to New York University, came from Germany. Timoshenko, who came from Russia and worked at Westinghouse. So most engineers have heard of Timoshenko because of his textbooks. And then von Karman, who was a student at Prantl and came to Caltech and got the aerodynamics program going at Caltech. In the Second World War, what happened was, this is when funding came into play. So the government started to fund research, right, during the Second World War. The pure mathematicians wanted to get some of this money, and they just said, go away, you don't know anything useful. Right? But what happened was the private schools, the private universities especially, started to build out applied math programs at that time. So let me start to go a bit quicker. So the first American applied math journal started in 1946. SIAM was founded in 1952. It currently has 13,000 members, whereas the American Math Society is much older, you see, 1888, and bigger, still bigger. So until recently, I'll have to qualify recently in a minute, but the American math department, so here I'm thinking really of big math departments in big state schools, right? They tended to disparage applied mathematics, and this is typical. This is Paul Halmos. He's a very well-known American mathematician, very good writer of mathematics. And he wrote a paper, an article, and this was the title of the article, Applied Mathematics is Bad Mathematics. And he was really picking up the theme, if you like, from Hardy, who was an English mathematician. And he said, most of the best mathematics is useless. Right? And Hardy wrote a book, in fact, which is called A Mathematician's Apology. And his idea was that, if you like, whatever he'd done in mathematics, he never hurt anybody. That was his justification. He never hurt anybody. He always thought that if you did any mathematics that had any use, you shouldn't do it. Right? That was his attitude. After he died, a lot of the work he did was used. Right? So he's probably turning in his grave. Okay, so now I'm up to step two. So step two then is the solving of the equations. And this is kind of the traditional role of applied mathematicians, if you like. Right? So a student comes and knocks on my door and says, I've got this problem, can you solve it for me? Right? And so, I mean, it's good that we do this. So it's part of our function, if you like. Right? It's a kind of, what's the word here? So we are enablers. I think that's the jargon. Okay? So a student comes along and we say, oh, yeah, that's easy. You do this, you try that, you go and look in this book, you go and read this paper. So those sorts of problems, they fall into what I would call my domain of triviality. Right? And so we all have those. All faculty members have those. There are kind of regions of expertise where if a problem turns up in that area, you know how to do it straight away. Right? And you can tell someone what to do. But if it falls in a different area, you probably have no clue at all. Right? And You know, if someone came to me with a question about chemistry, I'd say, I've got no idea, I don't know about chemistry, go see somebody else. Okay? But then there's kind of fuzzy area, right, where there are things where I might know a bit, but not everything. Okay? So we all have these domains of triviality. So here's me in my domain of triviality. Okay? So the idea, this is what makes my life interesting, is when problems come along which are not in here, right, but they're out here. Right? And I like to see problems which are somehow close to my domain of triviality so that at least I can get started. Okay? And write my 10 pages of LaTeX. So, and the reason for doing that, so the reason for being interested in, I'll call them non-trivial problems, is that in the process of working on those problems, you can often generate new mathematical tools, maybe new algorithms, new collaborations. I mean, the idea of a good collaboration is where two people get together, or maybe more than two, and they have different domains of triviality, but there's a little bit where they're kind of close, and then between them they can do something much better than either of them could have done together, individually. Okay? And also problems for students. So we always need good problems. So now I do the last three steps I do together. All right? So the last three steps were make a prediction, compare with experiments, if necessary, go back to the beginning and revise. Okay? So let me see what I say here. So we solve the equation somehow, maybe approximately, maybe exactly, maybe numerically. We try to extract some property of the solution that can be compared with experiments, right? And if the experiments have been done, we do it, we make the comparison, and if they haven't, maybe we can encourage someone to do them. So if they don't agree here, what would you do? Well, the first thing you do, right, is you say, well, there's probably a bug in my code, right? So you go and play around with that, right? And then if you're happy with the programming or the calculation, you check that you haven't dropped a minus somewhere, right? Like my students in complex variables. If you're happy with that, right, then the only explanation then is that, assuming the experiments are good, is that the model was wrong, right? So you have to go back to the beginning, right, and think about the model. Maybe I threw something away that was important, okay, that I thought was not important. What about if they do agree? Of course, you write the paper and send it off, right? If the experiments and the computations and the theory agree, then you say, oh, that's great, I'll send the paper off. But what you also should think about is whether you can break the agreement, right? So students are very reluctant to do this, all right? So if you have a piece of code, for example, that generates solutions to a problem where you think you know the answer and the agreement is good, students are going to say, okay, I'll write the thesis, okay? But it's important to try to break things, because you often learn interesting things by trying to do that. So I can say, I think, that applied mathematicians can contribute to all these steps, right? And in fact, there are some math departments that have labs in the departments, right, specifically for this purpose. Look, there aren't very many, but there are a few around the planet that do this. Okay. So now, why might you need applied mathematicians? So I'll start with this. I'm allowed to make jokes, right, about mathematicians, but you can see that this also makes jokes about other categories of people. But I think this is pretty good. So engineers think that equations approximate the real world. Maybe you have to decide for yourself if you agree. Physicists think that the real world approximates the equations. I'm not sure about that. And mathematicians don't care. So, as I say here, right, as with all good jokes, it contains a grain of truth, right? So I think that a good thing about applied mathematicians is that they are carefree in the following sense. They usually don't really care what the answer is, right? So some mathematicians would disagree with this, but this is how I think about applied mathematics, right? So this is an opinion now, okay? And that is that I don't really care what the answer is. I don't really care if the answer is 2 or 3, right? All I want to know is how to get the answer reliably, efficiently, accurately, okay? So it's really the process of getting the answer that's important. Okay. I am, of course, interested if the answer doesn't agree with experiments, because then I might have to go back and change the equations. Okay. But the answer is what it is. Right? I don't really have any agenda to worry about. Right? So I think this makes applied mathematicians useful, because they don't have any bias. They're also skilled, I think, at exploiting connections, because often mathematicians, applied mathematicians if you like, work in different physical domains, right? So for example, I work in, say, I showed you the problem with the cable, but I work in, say, water waves and Maxwell's equations on different kinds of physical areas, right? And I'm interested in the connections between those areas, like how the equations have things in common, right? That's a good thing, because often if you can solve an equation over here, then maybe you can just walk over here and solve it again, and no one knew that you'd already done it over there. You get 2 papers for the price of 1. So what do they need? What do applied mathematicians need now? This is to thrive. Apart from time, all right? So apart from time. So I read the list here. I'm not sure if this is in. I'm not sure that I would, stand by this ordering, but I think it's a decent ordering, right? So the first thing they need is problems, right? You need colleagues, right? So you need people that you can talk to, right, about mathematical things. So they might be colleagues in your department, but they might also be colleagues on the other side of the world that you can communicate with by, email or something like that, or through conferences. You need a good library. Definitely need a good library. The librarians here will be happy about that. But I think that's absolutely crucial. You need access to what's being done and what's been done. And you need students. Right? You need students to write the programs. Right? That's what students are for. And you need coffee, and you need beer. So other characteristics. So one characteristic of mathematicians is that they don't tend to work in big groups. Right? They don't tend to sit down and say, well, there's 6 of us here, let's try and work on this problem. It doesn't work like that. Okay? Never works like that. So I think it's fair to say that research groups in mathematics, they're fictions. They're only created for administrators. Right? I have tenure, so I can say these things. But that's not how first-class mathematics is done. It's not by all getting together in a group and working on something. It doesn't work like that. So, but one benefit of this structure, or this lack of structure, right, is that they are agile. I think that's the jargon word, right? That means they're not really invested in any, I don't have to have a big lab of stuff, right, or huge computers or whatever. So that means that I can easily dump that problem and walk over here and work on a different problem, right? So I'm agile in that sense. Right? I don't have huge investments in the problems I'm working on, apart from my time and that kind of thing. But I don't have like an army of students that need to work in this lab, and I'm always worrying about how to find the money to keep them all going. So the idea here is that to do first-class work, what you want are first-class problems, right, and the facilities around you that enable you to work on those problems. So I can say here that the consequence of this is that most mathematicians don't have or need a vision or goals or any of that stuff. Right? They don't need any of that. Right? What they need is to be able to work on problems, right? And they'll work on a range of problems, right? A range of difficulty problems, right? So there'll be kind of basic level, I call them enabling problems. A student comes along, knocks on my door and says, can you help me with this, right? I like to do that. But also, they'll also be working on problems which I say here are possibly impossible, right? So which I think is a good way of classifying them, right? You don't know if it's going to work out or not, right? That's another benefit of having tenure, right? You're allowed to work on problems which maybe don't come out, right? That's part of your job. Part of my job. So I finish off here by saying that their usually unstated goal is to do first-rate, non-trivial, timeless work. Right? I want people to be referring to my papers in 20 years' time. So now I can see it says advertisement. So I can tell you what we offer in my department. So at the moment we have 10 regular faculty, and we've got searches on for more. And what we know about in the department now, right, we know tons of stuff about differential equations and how to solve them, problems that are represented by differential equations, and also in applied statistics, which I know nothing about. Right? So some of your problems now, right, might fall into our domains of triviality. So don't be too shy to ask. I'm talking to the faculty there. Of course you are. So you should, in that case, you just send your students along, right? Right? So in my experience, at the moment I'm on like, I don't know, 25 PhD committees, right, different departments, right? And it's much more interesting for me to deal with the students, right? Because the students are more open to, oh yeah, no, I'll go and try that, or I'll go and look at that. And so, you know, the old faculty, they're much more set in their ways, right? Like I am. And I'll finish off with this picture here. So Pythagoras said that mathematics is the way to understand the universe. So this is, I don't know whether this looks like me, but I quite like this picture anyway. So I will stop there and get back to my beer. So thank you.